Okay, our next speaker is Dr. Narayan. And I heard him talk at the ASHS, it's the American Society for Horticultural Science. That's a conference every year. And last year it was in Miami, and I heard him talk, and I was so impressed with what he had to say about bioplastics. I decided I was going to try and see if he would come here. He's a very busy person, and I'm extremely honored he's here today. He actually flew in this morning from Washington, D.C., and he's flying back at 5 o'clock today. So I'm deeply, deeply honored he's here today. And as for his resume, he is a chemical engineer. He's from Michigan State University. He's a distinguished professor. And according to Dr. Carol Miles, who's our next speaker, he's the best in the world on bioplastics. So we're deeply honored to have you here. So, and about his bio, it's fairly long. It's a condensed bio, but I'm going to condense it further for you. He has more than 150 refereed publications, 28 issued patents, edited 3 books, all in the area of bio-based and biodegradable polymeric materials. He serves as a scientific chair of the Biodegradable Products Institute, North America, and he is the director to Society of Plastic Engineers, Bioplastic Special Interest Group, and he has served on the board of directors of ASTM International, a premier international standard-setting organization, and currently chairs the Committee on Environmentally Degradable Plastics and Bio-Based Products. He serves as a USA technical expert to ISO, which is the International Standards Organization on Plastics, and is chairman of ISO TC 61 SC1 on terminology, and convener of Working Group 23 on bioplastics. He's also convener of the Working Group 7 of ISO on packaging and the environment. He has testified before US congressional hearings on biodegradable and bio-based plastic issues, and worked with the United States of Agriculture on its Bio-Preferred program. That's a program for the federal procurement of bio-based plastics. Currently, he serves on the board of directors of Northern Technologies International. It's a 150 million publicly traded microcap company, and on CocaCola's Plant Bottle Advisory Board. He's also served on the technical advisory board of Tate and Lyle, that's a world-leading manufacturer of renewable food and industrial ingredients. He has won several awards, named Michigan State University Distinguished Professor in 2007. That's the highest honor that can be bestowed on a faculty member by a university. He has won the Governor's University Award for Commercialization Excellence, University Distinguished Faculty Award 2006, Withrow Distinguished Scholar Award 2005, Fulbright Distinguished Lectureship Chair in Science and Technology Management and Commercialization, DuPont's Packaging Award for Excellence in Innovation and Sustainability, 2010 as part of Coca-Cola Plant Bottle Team, and he's the first recipient of the William N. Finley Award for significant contributions to the application of new technologies and the Award of Excellence for exemplary technical contributions and valued leadership in ASTM Committee D20 on plastic. He has also won the James Hammer Memorial Lifetime Achievement Award in 2006 for outstanding leadership and research accomplishments in the field of degradable polymers from the Bioenvironmental Polymer Society, as well as the first recipient of the Lifetime Achievement Award 2010 from the BEPS. So he's won several more awards. I'm not going to go over the entire list, but he's a successful entrepreneur, having been responsible for commercializing several technologies. 2012 Tex Frazier, and of course that's where I met him when he did the 2012 Tex Frazier lecture at the National ASHS conference. We're indeed honored to have you here, and actually he's from India, my neighboring state of Chennai. So welcome, Dr. Narayan.
Thank you. You can keep it on. Thank you very much. After the way Leah set it up, I better not fail you, right? Yes, sir. No.
What do you do for fun?
This is fun, right? No, it's a pleasure here. Beautiful campus. I always thought Michigan State had the best campus. Now I'm not so sure, And you also have the sun out here. We got snow still out there, so that's that. Well, it's a pleasure to be here. And what I wanted to do today is to kind of challenge you, make you think outside the box. You're all involved with horticulture. You grow tomatoes, you grow grapes, you grow this. But what I want to submit to you is that maybe you will be growing plastics, right? And I would like for you to think outside the box. Maybe you will grow the plants the right way that will provide the chemicals, the biochemicals, the monomers, which will go into making the future plastics. That oil will not be the driver, but plants will be the driver, okay? And that's really where we are taking you to. And that community colleges and the researchers and your students should think that way. And I hope that you have programs where you don't talk about just growing crops and feeding the people, but you are good enough and bright enough to not only feed them, but clothe them and provide them the tools of material science that they can use, right? And that, I think, is the challenge, and that is the growth, and colleges like this can play a great role to do that, right? So I'm going to show you snippets of that, but in order for you to do that, you need to know the fundamentals, right? I'm sure you teach your students that, right? If you don't know the basics, if the building block is, the foundation is not strong enough, then whatever you build is going to come crashing down, right? And that's what I want to do with. So I want to challenge you. I want you to think outside the box, and I'm going to show you examples of what that is. So I'm going to talk about plasticulture, the use of plastics in agriculture, which you do as an example, but suggest to you that it's broader than that. And whenever I hear the words, when I go to such conferences, you use the word plastics, and that's it. And I'm saying, wait a minute, what plastics? What does it do? What kind of materials went into it, so on and so forth. So let's start. So the use of plastics in horticulture, for example, this right? I'm not going to teach you this. I just put it up for you as background reference, right? It's used in mulch film greenhouses, small tunnels, large tunnels. I never heard this word till I met Carol, who's going to speak to you about this in more detail later. But all these fruits and vegetable coverings and other uses, right? And then this is what supposedly the plastics do, and I believe you, right? Otherwise I wouldn't be here. So increased yields, harvest, reliance on herbicide, pesticides, better protection, better water conservation, all of those things is what you do. Improved product quality, optimized growth, weather changes. There's all sorts of wonderful stuff which plastics helps agriculture with, okay? And 5 million tons and growing. It's one of the biggest markets, and I'm surprised that this market is least understood by the people who use it and can have great opportunities for teaching, for research, and for actual commercialization, okay? So what's the problem? A problem is an opportunity. I'm an entrepreneur, and when somebody says something is a problem, you want to look at it, what's the opportunity for you to make money, right? Entrepreneurs like to make money. They dream about chasing the money. The money is really not the issue, it is the dream of chasing it, right? That's really what is so exciting about it. So the major issues, and you've heard this word, carbon footprint, right? You've heard this word, carbon footprint. Everybody on the street knows about the carbon footprint now, right? And so what we are saying is that we're going to talk about the carbon footprint because after all the products you work with has carbon as its basic skeleton, right? Whether it's a tomato or it's either cellulose, it's protein, it's carbohydrates, they all have carbon as it. The plastics also have carbon. So if I break it down to the very small element, you grow carbon-based products, and I do carbon-based products. We should be all in the same camp then, right? You make it a little different. You make it much more tastier, more sweeter, You know, it fills your stomach, it makes you feel good, but you also cause all sorts of problems as well. In plastics, the same way. It gives you all sorts of values, but it has its problems. And these are the problems. Number one is what I call the material carbon footprint. So this is your education right now. Why do I call it material carbon? I'm talking about the origin of the carbon in that product. And you use that carbon to make your products, but the plastics industry uses petroleum or fossil resources to make that same carbon products. So think for a minute, if I made your tomatoes from fossil fuels, you wouldn't like to eat it, would you? But it's possible, right? Synthetically, we could do that. By the same token, why do we want to make plastics from petroleum fossil when I can make it out of the plants and the biomass which we grow? And that is the challenge, and that's what we're trying. Why use petroleum and fossil fuels, which is grown, which is found in the ground in very volatile regions where you have to fight wars to keep it coming through? What if you diversified it, whereas 50 to 60% of everything we use for energy, for buildings, for clothing, for all of this comes from crops? Then nobody would be debating on what's happening in the Middle East or anywhere. We would be self-sufficient. And that's really what we are talking about. So that is what I call the material carbon footprint, the carbon's origin. There is also what we call the process carbon. When you have this feedstock, whether it's plants or biomass or algae or any of that, you have to convert that feedstock to your finished product. You are lucky. You know, the nature does it for you. You plant the crop and it gives you tomatoes. You plant another crop and it gives you grapes, you know. You just have to nurture it. We have to work very hard to convert it to a plastic product. Okay. So the process of converting it has got impacts on the environment, just like when you process or you nurture, you have impacts on the environment. The herbicides you use, the water you use, you have impacts. And that's what sustainable agriculture is, what you've been talking about. How do I minimize impacts? How do I reduce impact? Well, we want to do the same with the plastics industry. All right? So that's what we mean by process. Unfortunately, in these discussions, which is presented about process footprints, it is confused, or the material carbon is just brought into the same thing. So you're provided one big thing and said, is it good or bad? And we're debating about this process. Okay. The one which I wanted to most focus on was what I call end of life. What happens to the product after use when it enters the disposal system? When you grow tomatoes, or you grow, I haven't speak tomatoes because the last lecture was tomatoes and it made me hungry, and I saw all those red, nice, juicy tomatoes out there. I never get it, but seems like you guys seem to know what to do to get that. But when that falls to the ground, nature takes care of it. It biodegrades it. It becomes a part of the soil, and there is no issues with it, correct? So to you, the word biodegradation is similar to what happens with either the tomato or the stalk or the leaves, whatever. You plow it back into the ground. Plastics which you're using today, you can't plow it back into the ground. It'll be there forever. Or you have to come back and take it out. And then what do you do with it? You have to burn it. Where do you find the incinerator, right? So the most inexpensive, you use these plastics because it gives you all those values, and it is less expensive. So if I gave you a plastic made from plant mass and ask you to pay 20% more or 50% more, why won't you purchase it? It's your own product coming out of it. And that's something which even I cannot seem to understand, because the debate is that I got a polyethylene film or a film which is plastic, which gives me this, either keep the temperature cool, keeps the weeds out, whatever you're looking for, is also accessible with plastics made from plants. Okay, it's not there, but that's what I challenge you to say, that that's what we want to do. So what happens to it when you bury it in the soil? or you compost it, or you convert it to an anaerobic digester and generate energy which you will feed back, gives you back energy, right? I think that's the challenge. And while I am on that subject, I am going to talk about soil, because typically the way you consider these plastics, which you use as mulch films or to protect your food, fruits, you just want to bury it in the ground and make it disappear, right? Vanishing, that's, trigger like the movies, right? Then in 20 seconds it will just disintegrate and go away. That's what you want. But life is not that simple, so you want to be careful what you mean by that. Okay, so you can either collect it and recycle it, but when you got soil and other things, that becomes an almost impossible task. So you have to have either biodegradability in soil, that is, you simply plow it back into the ground, or you collect it and you compost it with other stuff you do, or if you're near a dairy farm or a hog farm or one, you have a lot of manure, which we have a problem. Manure management is a big problem. So people are setting up anaerobic digesters, which gives you energy, which you feed to a generator, and then you can put it back into the grid, and whatever residue is remaining, you compost it and you land apply it. A total solution. So my submission to you is, when you're looking at these biodegradable plastics, whether it's for the covering, whether it's for mulches, don't restrict yourself to something which you have to plow back on the ground. That's the ideal. But what if you can use anaerobic digesters in conjunction with some other waste? What if you can generate added income by composting and selling the compost to other places? That cost could be then added to the plastic. So I want you to, again, think outside the box, because typically when you talk agricultural film, they want to just plow it back on the ground, but I want you to keep that in mind. Okay. This, if you don't listen to anything else, you must listen to this. Whenever there is an opportunity, that's the first thing which happens. You got a bunch of people who come and sell you a bunch of goods. I got this magic dust. You put it in whatever you're doing and everything will go away. You'll be fine. You give me your account number and I'll make you very rich, right? You'll receive those pilching emails, right? And I hope nobody from this audience has signed up and given that, but that happens. That I want you to stay off. So understand the science of biodegradability. You are biologists. You should understand this very well. Anyway, that's the goal. Okay, so let's get started. So I'm talking about the beginning of life. I'm talking about switching the feedstock base from petrofossil to plant biomass, and that's the bio-based plastic. So you have to ask, why do I have to switch? What is the value proposition? That's one. Biodegradable plastics has nothing to do with that bio-based. And this is the first myth. Bio-based and biodegradable are used interchangeably. It's not. Bio-based has got to do with the carbon present in your product and its origination from plants, biomass. Biodegradability has got to do with microorganisms in the disposal environment capable of utilizing or assimilating your plastic product. Very different. Okay? That's what. But the key phrase there is what's written up there. Complete, total, and time of 2 years for your types of materials. In compost, it's going to be 180 days because that's how you run it. But 2 years or less. And the next point would be bio-based plastics are not necessarily biodegradable. Right? Biodegradable plastics are not necessarily bio-based. So just because you have this wonderful plant-based plastic doesn't automatically confer on it biodegradability. Okay? And there are petroleum-based plastics which you could design which would be biodegradable, but not biomass-based. So that's another learning for you to keep in mind. And unfortunately, the word bioplastics, you'll hear this word a lot. In fact, I think I was introduced as the bioplastics expert, Well, I cringe sometimes when I hear the word because bioplastics is the industry term to encompass everything because we want to claim the whole territory. So bioplastics means bio-based and biodegradable, or biodegradable and petro-based. Okay. So bioplastics doesn't mean it's from plant. So this is at least the take-home message here. Okay. So if I were to tell you, let's make these plastics from plants and biomass, you should rightly ask me the question, what is the value proposition? And to understand that value proposition, I'll take you back to basic biology. And trust me, I'm a chemical engineer. You're not going to see any differential equations, no integrals, and no complicated models to solve. It's going to be very simple, basic, and you'll wonder why the hell is this professor got this distinguished title when he talks things which I could have learned in high school, right? It's the way you teach it. That's what it is. So you studied this. Carbon present in the atmosphere as CO2. And for the students in the audience, you don't have to be very bright. You just need to know your basics. What you studied in high school can make you very rich and very famous. Right? So carbon present in the atmosphere as CO2. You provide sunlight energy. It converts the carbon to organic carbon or plant biomass. I call this the new carbon. This is what you do. You actually grow it. You make these things. What's key point to note is this sequestration of carbon to plant biomass takes place in 1 year. If you plant a crop, it takes place in 10, 15 years. If you have a tree plantation or a wood or some plant cultivation going on. Okay? Over millions of years, that organic carbon has been converted to fossil carbon. So it's not too unheard of when I told you I could make tomatoes from plants, from fossil, right? Because it's part of the same carbon cycle. Just think for a minute. And therefore, this fossil resources, which we criticize so much, is also part of that same carbon cycle. It is in this planet. It didn't come from Mars, and it's part of the natural cycle. So we can't say, and we still use this word, we say our products are natural, organic. These are the words we use. Well, fossil is organic, it is natural, and yes, it is renewable. Okay, millions of years. Right? But it is renewable, right? So what is the argument? Why you should switch? And the argument is pretty straightforward and simple. We use these resources to make whatever, our products, chemicals, fuels, and put it back into the atmosphere as CO2. We do it in a time frame of 1 to 10 years, 1 year or 10 years maximum. So that is the issue. The rate and time scale of carbon sequestration from the atmosphere to the resource is in millions of years. The rate and time scale of use and putting it back into the environment is 1 to 10 to 15 years. Very simple math. That's why I told the students in the audience, you don't have to be very clever. No differential equations needed to see the difference. It's not sustainable. However, if I used plant biomass as my starting resource, the rate and time scales of carbon sequestration balances the rate in time scale of use and putting it back. I'm in that range. And therefore, that, ladies and gentlemen, is the fundamental value proposition for using plant biomass. Short, imbalanced, sustainable carbon cycle. So tomorrow, if somebody asks you the question, why do I want to switch? Why should Kansas become the next materials revolution? That's because you can manage carbon better than Saudi Arabia or Kuwait or those guys can. They are not sustainable, right? That's the submission I make to you. Okay, so if you follow this argument, I will present it to you in a much more bigger impact way. Carbon emissions. Carbon is distributed in the environmental compartments as shown here, right? In the atmosphere, you have 730 gigatons. In the oceans, 38,000 gigatons, and the carbon in plants and vegetation and soils is about 2,000 gigatons. Okay, that's the distribution of carbon in these environmental compartments. And although I said I would not use high-sounding chemical stuff, I'm sure you studied the laws of thermodynamics, right? Maybe, maybe not. Well, one of the laws says that you cannot create matter nor destroy it. So you cannot take CO2 and make it disappear. You can just put it in different forms. So the issue is not CO2. The issue is managing carbon in a sustainable manner. And what nature has done best is to distribute carbon in different environmental compartments and cycle it so that they are sustainable. Look up the numbers. 88 gigatons goes back to the atmosphere, 90 goes to the oceans. If you look at plants and vegetation, 119 gigatons to the environment, 120 is fixed. Even you who actually do land use, you grow crops, you do all those things, even you are in balance. 1.7 gigatons, 1.9 you fix. That's how nature cycles carbon. And look what we do at the end. Fossil, 6.3 gigatons going to the environment. There's no corresponding flux fixing it back in a time frame that is sustainable. So that, ladies and gentlemen, between those two slides is the argument that there is the opportunity that if you use plant mass in a manner which is sustainable, then you will be managing carbon in a more efficient and sustainable manner. That is the driver for these bio-based plastics, bio-based chemicals, and biofuels. That's the driver. Okay, so I want to illustrate this in a very, what I would call mathematical fashion, right? I'm an engineer, so you got to give numbers. If you just give me all these words, I mean, it doesn't make sense, right? So I give you numbers for you. Polyethylene. Forget even if you don't know what is polyethylene, doesn't matter. You can see the red, you know it is carbon. So there's carbon in polyethylene. PET, that molecule which you see on the right-hand side, is what all those pop bottles and water bottles are made up of. Okay. All of them have carbon. And the question we are asking is, if I take those carbons and replace it from the petroleum fossil fuels, remove that and bring it from plant biomass, what is the value proposition? That's really what we're asking, correct? Okay, so those are the two carbons, and this is this new polymer called PLA. PLA is made from corn. It goes through a process, and we can talk about that in a minute. But here's where I introduce you to what happens. So if I made 100 kilograms of polyethylene, and I want to ask the question, if that carbon came from plant mass, what is my impact? And if that carbon came from fossil, what is the impact? Very simple math, right? And let's do the math. You studied this hopefully in high school. Polyethylene has C2H4. So for 100 kilograms of polyethylene you want to manufacture, there is 85.7 kilograms of carbon associated with it. Okay? You can do the math later and see that. If I burn this, carbon plus oxygen gives you CO2. 12 kilograms of carbon will give you 44 kilograms of CO2. So if I have 85.7 kilograms of carbon present in the backbone or in the tomatoes or whatever you do, I can calculate how much CO2 would be released if it breaks down and is completely biodegraded or degraded or burnt, whatever it may be. So 44 by 12 times 85.7 gives you 314 kilograms of CO2. So every time you make 100 kilograms of polyethylene or tomatoes, I don't know what's the number for tomatoes. Now I will go back and work out the math because this is a good way to present it now. So that will give you 314 kgs of CO2. If I replace that carbon with carbon from plant mass, I'll still put out 314 kgs of CO2. No question about it. But I plant another crop the next season, or I have a vegetation growing in the next 10 years, which will fix that CO2. I am zero material carbon footprint. Do you see the same equation which I presented? Short, sustainable carbon cycle, and this is millions of years to fix it, 10 to 20 years to put it back. That same thing, I am now explaining it to you in numbers, which you should be able to explain too. So this is the material carbon footprint. This, ladies and gentlemen, is the value proposition for you to not just grow tomatoes, but to grow plastics, because you are sustainable than fossil fuels. Okay. So, and this we can determine experimentally, and I'll talk about that in a minute later. So Brasscam is in Brazil, is now one of the largest polyethylene, polypropylene manufacturers in the world. They just acquired Dow's polypropylene business. And as you know, the Brazilian economy is going great guns because they have decided they would not focus only on fossil, they would also look at renewable resources. So Brasscam has got its own petroleum refinery on their doorstep. But they are also making polyethylene from sugarcane. So you grow sugarcane, you get sugar out of it, you ferment it to ethanol, the ethanol comes to the plant there, and they convert it to ethylene and make polyethylene. So that plastic film which you have could potentially come from a Brasscam plant making biopolyethylene. The material carbon footprint for this is 0. And you can work the numbers, 314 kgs of CO2 per 100 kgs. If you have 100 million tons, that's 314 million tons of CO2 being released. And if you use sugarcane base, that's 0. Look at the savings you suddenly start to see, and that's why Brasscam does this. They are manufacturing bio-based polyethylene. They are moving to taking their bottles and trying to first replace the carbon, which today comes from petroleum, with carbon from sugarcane or carbon from corn, because that impact of that carbon CO2 will be 0 if they did it. So if I used, right now they can only make 2 of those 10 carbons from plant mass. The remaining 8 is still coming from petroleum. Eventually, they expect all 10 to be. But even with those 2 carbons, we get a number as follows. 37.5 million metric tons PET is used just to make these bottles which you use a lot of, okay? So if I replace only 2 of those 10 carbons, 20% bio-based carbon content, you will save 17 million metric tons of CO2. And that translates to 40 million barrels of oil per year savings if you did this. Just 2 carbons. So you look at the impact if you multiply and grow it. This is what drives CocaCola in terms of sustainability. It's what they want to go, and they have moved very much forward with this. These are some of the bottles. PLA is another plastic resin made from corn. This is also biodegradable and compostable. Okay, so so this is one of our big contributions, because it goes back to the human nature's, I think, intrinsic nature to cheat, if you can get away with it. Whether it's the taxes or it's your anything. Maybe I'm wrong, I'm getting into philosophy here, which I shouldn't probably. So if you don't agree with it, don't hold me against it. That's not my area. So I don't have a degree in anything of that, so you can give me a little loose thing there. Okay, so if I made a polyethylene film and told you this is bio-based, you're going to trust me and say, oh, absolutely, you told me so, therefore I'll take it, right? And the answer is, no, you should not. You've got to have a proof that, how do I know this is? So we came up with a method where we used a simple radiocarbon dating methodology to do that. So in nature, CO2 in the environment is in equilibrium with radioactive carbon, all right? the half-life of radioactive carbon is 5,730 years. Okay. Therefore, all of the plant-based carbons has this radioactive carbon signature associated with it, including yourself. Okay. All the proteins, all your tomatoes have that. I can analyze it, and I can tell you how much of that bio-based carbon is there. Petroleum carbon, fossil carbon, is created over millions of years. It has no bio-based carbon. I mean, it has no radioactive carbon. So we use this method to clearly establish whether a product has got bio-based carbon and how much to an accuracy of plus or minus 3%. Think for a minute. You're growing something on the fields, and I make this plastic product after a lot of steps. And I can measure this C14, C12 ratio, compare it to another standard, and tell you accurately, plus or minus 3%, how much bio-based carbon is really in this product. And that really revolutionized this industry, because now there's a level playing field. You can't say, well, I measured it differently, and I got 30, and he didn't measure it right, so he got 10. Those things are all eliminated. And the USDA BioPreferred program is based on this standard. In fact, this has now become the de facto world standard to measure bio-based content. So you have companies like BASF, DSM, Rocket, name a chemical company. They are now talking about working with bio-based products. Okay, so that's the methodology. And then this is just the carbon footprint, and I'm going to skip this because of time, but don't worry about what I put there. I just want you to keep in mind that this alone is not sufficient. So just because you make plastics from your crop, and then in the process of converting that crop to your final product, you spew out all sorts of emissions and you consume 10 times more energy, then you have achieved nothing, right? And that's where this LCA and all these things come into play, okay? But the reverse is also not true. Just because somebody comes up and says your LCA is bad, therefore all products from plant biomass is useless, does not fly, because the material carbon footprint is 0. So you have to come up with the right process to convert it, but inherently, intrinsically, a plant biomass resource is going to give you a 0 material carbon footprint. A fossil petroleum resource will not give you that footprint. And the numbers could be pretty significant, and that is the value proposition for this. Okay, I'll skip this. I wanted to put this up just to show you that I can use LCA, and you'll hear a lot about LCA, to make anything look good or bad, depending on where you draw the boundary conditions. Okay? And so you have to be very careful about it, and I won't go into this in detail. Maybe you need to invite me again to talk about this. I have to, whenever I go, I have to keep some things away from you so that you don't forget me and then you call me back to teach you that. Okay. So let's talk. So this is what I call the beginning of life. Okay. Now let's talk about end of life. What happens to product after you want to dispose it of? So we have to either design for recovery by recycling. I see all those recycling bins here. Although I wonder how much of it actually gets recycled, or you have whoever is the garbage collector collects it and he says, what a pain, dump it all in the landfill, and that's the end of it. Somebody has to watch it. I trust me, half of it probably goes in the landfill because you don't look at it. Now, as being cynical, am I not? But I did this in Michigan. At least in Michigan, that's what happened. So I'll exempt Kansas from this question. Okay, so you can do recycling, or you can design for biodegradability, right? So this word biodegradable is, I've been using it, you have been using it, and anybody who comes and tells you, oh, it's biodegradable. What is biodegradable? And that's what I want you to clearly understand and do it. So when you talk about biodegradability, you can't talk about it in the extreme. You have to define what disposal environment are you talking about. Is it soil? Is it composting? Is it anaerobic digestion? Is it marine? And in what time frame is it going to be completely biodegraded? 1 year, 10 years, 100 years? Because all of us are biodegradable sometime or the other, right? So we can all put a big label biodegradable and walk around, but the reality is when we're talking about the environment, we're talking 1 year, 2 years, and it must be completely removed from the environment. So my submission is that this term biodegradability is the most misused, abused term. And the question you need to ask yourself, and whoever comes to you, is, can microorganisms present in that disposal environment completely utilize this as food? That's what they do. They don't do it because they want to clean the environment for you. They need food, that's why they consume that. So can they do it, the biological process, and what extent, and in what time frame? So if only 10% is gone, 20% is gone, and 80 remains, you have done nothing. Okay. Oh, by the way, many of you are taking notes. I'm going to make this available on your website so you can download this presentation and everything else. So I want good ambassadors to promote this correctly. So that's what I'm trying to do. I have a vested interest here. So what extent and what time frame? And you must have complete microbial assimilation in a short time frame, otherwise you'll have problems. All right. Here is the take-home message. Degradability, partial biodegradable is not acceptable. It has very serious health and environmental consequences. Okay. So you would think, well, 20% biodegradable is better than 0, is it not? Or 50 better than 0? Why do I need 100? I've done something good. The answer is you have done something bad. You either have it completely biodegradable or it's not biodegradable. There's no in-betweens, right? You can't be half pregnant, is what I'm saying here. You're either pregnant or you're not. You're either completely biodegradable or you're not biodegradable, okay? Why is that important? And these references, I would let you look at it, but I'm going to show you some of that. That's China. These films, this is straight out of what you would happen if you follow that degradability concept. They have these mulch films, which they used a lot in China, which was very thin. So they were degradable. They made dust, and they used to have plastic dust floating all over, and you can see places in the mountains where plastic dust has accumulated from agricultural mulch films. That's what you see there. And you don't want that, okay? This is visible. This is invisible. Suppose you have a little pellet which is broken down, you can't even see it. Now that has food growing over it, so birds come in and eat it. So now a little plastic pellet gets into the digestive tract of birds, or fishes eat it. And then the toxin with the plastic goes into the fishes, you eat the fish, and the plastic toxin goes up the food chain, okay? So this is actual evidence, right? And I'm going to just put you the last one. Japanese researchers found that plastic pellets, degraded plastic pellets, had more toxins on it than background levels. And if you are following the literature, just recently, Chelsea Roman, she works with me in NCES, which is the National Center for Oceanic Research. She found with a lot of evidence that polyethylene, polypropylene, and polystyrene had a lot more of these toxins. They by themselves are not toxic, but because they can absorb these, they concentrate. It's like a sponge. And so now suddenly toxins are collected and are part of the food chain. What I am submitting to you is either you have to make sure that it is completely utilized and removed, or don't make it degradable at all. And that is the challenge which you should look at. So, how much time do I have? You should never call me. Okay, good. All right, so I'm always running against time, you know. All right, so what does biodegradable mean? It doesn't mean you just break it up and disintegrate it. So you can do that. Okay, you can get all these fragments, and you can't even see it. You know, if you take polystyrene, that styrofoam, you know, where you buy some of whatever you buy, and you crush it up and make it brown and crush it up and throw it into your soil, you couldn't tell the difference. Okay, but that doesn't mean anything. Degradation is not biodegradation unless you can prove that those fragments are completely assimilated by the microorganisms in that disposal environment. You'd agree with me on that, right? So if you want to claim biodegradability, you can't show degradation and molecular weight and FTR and all these spin things around it. Show me that microorganisms are utilizing it. And in what time frame and in how much or what extent. So that's my first message to you. Remember that. Biodegradability is microbial utilization. And you have to prove that. So how do we measure this microbial utilization? And you do it. You studied this in biology. And so I'm not sure why we still debate it, but here's what it is. So microorganisms utilize carbon for food, for energy, to drive their life processes. They don't do it to clean up the environment for you. So if you want to prove that microorganisms are utilizing it, what is the biology which drives this life process carbon utilization? Well, the way microorganisms do it is they transport this inside the cell, and so the ability for it to be transported is important, which means large molecules will not definitely make it. Once inside the cell, it oxidizes it biologically through a complex series of mechanisms to CO2. This is an exothermic process which releases energy, minus 686 kilocalories per mole. And that is utilized by the microorganism for its life process. I had to throw in that this is thermodynamic and exothermic just to let you know I am a chemical engineering professor, right? So you don't have to remember that part. All you have to remember is that microorganisms utilize it, generate energy for their life processes. That you can remember, right? That's what it does. So if I want to prove that, and in an anaerobic, so if I want to prove that microorganisms are utilizing it, I feed it carbon, your plastic carbon. I look up to measure the CO2 coming out, give it no other carbon food except plastic carbon, and if the microorganism is utilizing it, I should see CO2. And the percent carbon inputted as a function of the CO2 generated will tell me how much of my carbon is being utilized. That is not rocket science. But we never ask that question. We just believe whatever somebody tells us, and this has become a big racket in this area, as Carol will testify. She actually has tested some of these films and done that. So this is biodegradation. If you do it under anaerobic conditions, you'll get CO2 plus methane, and that's what it is. So very simple test. This is what the basis is. So microorganisms, this just summarize it. I will go over this real quick. You can look up this later on. Thus, a rate of CO2 in an aerobic environment, or CO2 plus methane in anaerobic, gives you how much of your carbon is being utilized. So ask for the data. It's as simple as that. And what is the methodology? So I will leave this up. You take a flask. This could be done in this community college tomorrow, right? Because you have a lot of students, and students can do a lot of work. If you don't give them work, then they get spoiled. So, so you got to put them to work. So you just get a flask, pick up the soil, all right. Make sure there is no other carbon in there. There are lots of microorganisms. You don't have to give it any microorganism. Take your plastic film, put it in there, and then the CO2 evolved, you trap it in some solution, and find out how much of the carbon is being converted to CO2 as a function of time, right? That's the axis there. So you should be able to show that 90+% of the carbon is utilized if that carbon has come out as CO2, right? You could do it in this college, you could do it in your backyard. Right? That is what is needed, and this, ladies and gentlemen, is the basis for all the ASTM and ISO tests. I became very famous, infamous, whichever way you want to do it, by just writing this up in a standard. Okay, but I could have done this, any high school biology student could have done this as well, right? But basic principle is what I'm trying to tell you. So most of the ASTM standards you read about, very long, It teaches you exactly how to do it. But the fundamental biology is this. Can microorganism utilize carbon? So feed it your carbon substrate. Don't give it any other carbon food. Give it all the nutrients, the moisture, whatever else it needs. And then if the microorganism is truly utilizing that carbon, you should see CO2 evolution. You measure CO2, you know how much carbon you have put in, you got the percent microbial utilization of your test material. If it is in soil, it is soil biodegradation. If it is a compost matrix, it is compost. If that was an anaerobic system, then you would be measuring CO2 and methane. That is the basis for all of that. And so the requirement of the standards is 90% plus of the carbon should be utilized by the microorganism. One of the mistakes we made early on, if I had my wish to go back, I would never have used the word biodegradation, because degradation means just goes away. I would have used the word microbial utilization. That's a harder one to fool, because you're looking for utilization of the carbon. You're not looking for degradation, which need not necessarily be biological. That's the problem you have, and therefore we do it this way. Okay, just visually, I'm just showing you this to show you that if you have a polyethylene film, nothing happens, but if you have the right compostable biodegradable material, you won't see anything. Caution, just seeing this alone doesn't mean your product is biodegradable, because it could have just fragmented and you can't see it. It is the CO2 evolution which must be the filter for any biodegradability. All right. So these are standards, and I'm going to skip these couple of slides. And I put it in there just for you to read, right? You know, a professor is a good professor is supposed to give homework. And I can't check your homework, but I trust you'll do this. You'll do the reading, and you will know what I'm talking about. So these are the standards which tell you what is a method, how do you measure it. We have specification standards, as you can see, for all European, international, ASTM, they all have the same way. I mean, all the standards say the same thing with minute differences, so you won't go wrong, whatever standard, specification standard you would pick up. Okay, so these two slides, because I want to give you just one more set before I do it, is to tell you that there are test methods and there are standards. Here is where the problem is. And I'll just give you one illustration, which is in this slide, but just pay attention to what I say. If somebody does a test method, there is a number, ASTM 5511. They come and tell you, there are people in the marketplace, we tested it by this method, and it is biodegradable. Okay, ask for the data. Because a test method just teaches you how to measure it, right? You took the exam, but you don't tell whether you passed or failed. And you say, give me credit, I took the exam, right? I don't think anybody will give you that. Same principle here. They may have done the test. The test is not, did 10% biodegrade or 20% or 50%? Oh, don't worry, everything will go away, trust me. That's what you want to be careful about. Test methods can be 0, 50, or 100. You should see the data, and this is the reason why this is important. Okay. My favorite, you heard the term greenwashing, right? And you will get greenwashed. The more these products become more important, more valuable, every one of you are going to be approached by some company, hopefully not me, or maybe I should do it just to test you out. You know, I have this magic additive, I put it into polyethylene, and it will magically make it go away. Is it biodegradable? Oh yes, it is. 100%, 9 months to 5 years. And you say, oh, maybe that's good, I'll take it. Data, proof, and you should do it yourself now, because now you can simply draw. Excel gives you beautiful line drawings, which you can make it look so perfect that you'll believe it. So you must do your data by yourself. Okay. I'll give you a couple of examples, and then I'll stop here. This is a company which claimed if I make a master batch, that means I have 50% of my additive in a polyethylene film, it will biodegrade completely. Okay, that's the claim. The lower line, which you see, it plateaus out at 20%. How can this material be claimed to completely biodegrade in 9 months, 5 years, or 20 years? Look at the level of the graph there. But that's the claim. It will biodegrade in 9 months. That's what you have. Okay. How do you do it? It's something I hope no Johnson Community College student ever does, right? You draw the line, you stop the experiment before it starts to flatten out. And then you drew a linear extrapolation of that line. And then you say, of course, 90%, look at that, perfect line. I can tell you how fast it does. That's what you must be at. This is what is happening in the real world. It's unfortunate, but it's true. And in the US, it's not so, but now people are going to Africa, to India, to China, and providing this. And that is, but you need to be aware of that. Here is something. 12 to 24 months, it will completely biodegrade. So these abstract, non-data specific claims should be totally thrown out. Okay. I want to show you this last one because I want to leave you a little bit with questions is, it's even scientists are doing this. And you wonder why. You are reviewers, some of them. Why do you allow this? This is a paper which was published in Chem Communications, a very good peer-reviewed journal. The scientists took polyethylene and grafted sugar on the backbone. And their claim is the grafting of sugar greatly enhanced biodegradation. It went from 1 to 2, 50%. So here's statistics. If you go from 1 to 2%, it's 50% increase, right? But it has no meaning. That's how it is. So they have greatly increased, and the data shows only 2 to 12% weight loss. Look what the press did to this report. Sugar turns polyethylene biodegradable, makes a meal of sweetened polyethylene and polystyrene. So take sugar, put it in with your plastic film, and the microorganisms will come in, and magically it's going to take the sugar and secrete enzymes, and the carbon-carbon backbones of polyethylene will completely be assimilated. That's what you're being told, right? And that is a Chem Communications paper. This is what is happening, and it's still happening today. So I've got, I don't know, 50, 60 people here. The next time you see, you want to watch out for these kinds of things. True data, where carbon is being utilized, is what you want, all right? The Federal Trade Commission just issued guidelines recently on these. And they're absolutely in sync with whatever I've told you so far. If you want to make an unqualified claim of biodegradability, you must prove with clear scientific data that all of that carbon will be converted to cell biomass, CO2, and water within 1 year or less. If you don't, then you are misleading the public. That's a clear statement from the FTC. And you know, educating lawyers can be very, very hard. And they got the message very good, so I'm very proud of that fact. Okay. They also said, if you want to make unqualified claims, this is what is this, you can read it, then you must provide the rate and extent of degradation, just like what I told you. So if you want to say my product is 30% biodegradable, then you must say in what time and provide the data to back it. The data should be based on credible scientific evidence, which is third-party certified. You follow the FTC guidelines, you cannot go wrong. In fact, that's where that statement is. And I won't read out this take-home message, but that's the homework for you, okay? I want you to read this at your leisure. You've got a lot of time, I presume. And it essentially summarizes for you what all I've told you. I hope I've left you with some few nuggets for you to think about. And I thank you very much for inviting me. Thank you very much. Sure, go ahead.
I have a question, Dr. Narayan. This whole process sounds very promising in terms of getting plant-based materials
Yes.
to develop plastics. But I have a concern about the development of your green carbon. You mentioned this company in Brazil that is
Brasscam. Yeah.
sugar cane and so on. From other things we've been reading, we hear that the Amazon forest is being taken down in order to grow more of these crop plants. So
let's address that right off the top of the bat on that question, and then we can go to your next. As the president of Brazil said in the United Nations, sugarcane is grown in the opposite end of where the Amazon forests are. They already have those forests. They cleared it up a long time back. There is no Amazon forest being cut to grow sugarcane. That's the reality of it. I'm not sure south or north, but it's totally in different regions. Okay, come back to corn as the example. This is another, I would say, a myth. And people in Kansas, Michigan, and all should realize that. Let's for a minute take this. Corn is grown, and I know Michigan better, so, and you don't know it, so you can't question me much. So I'll take Michigan as my example. Corn and soybeans are grown in the upper or in the thumb area. It's not grown in Lansing, Michigan, or Detroit, Michigan, or Ann Arbor, Michigan. So you say, oh, they're growing corn, they're using land, they're polluting everything, we should stop that. In the sustainability equation, people are a part of that. So we are saying that those people should stop growing crops, farmers, and come to the cities and create a bigger environmental burden. So farmers are productive, like you are. They grow crops. If they can create more value-added products out of that, that's more revenues to them. It stabilizes their base. And yes, you must manage it correctly. So, I put it this way in a very harsh terms because these kinds of myths float around. For example, there was this big food issue in Egypt, and corn was blamed for it. But that was wheat. What had corn to do with it? Okay, Kansas could have been blamed, but not the entire corn belt growing it, right? Same with Mexico. They use tortillas, the blue, that is food corn, not feed corn. And majority, 90+% of US grows feed corn, not food corn. So yes, we need to make sure that we manage it sustainably. But what I am saying is, based on my carbon cycle, that it does make sense that both humans and agriculture can exist in harmony and provide good carbon management. And unfortunately, I didn't look at the Super Bowl commercial, but that was an ideal commercial for the farmer. You guys see that? Yeah. I should play it now. Yeah. Okay, I will answer it to you in two ways. Okay, the first way, and I didn't have the slide, that's why you got to invite me again, I'm saying. But the problem there is, here's what happens. Let's say you sequester it. You sequester everything, so no carbon is released to the environment. Okay, but if I use biomass, I'm sucking carbon out of the environment. But if I use fossil, so if the baseline is 0, like you suggest, then plant-based is minus 314, right? So I'm still better than petroleum-based. That's the simple answer to it. But the reality is, sustainability is always a cycle. It is never a one-way to anything. You look at the natures, biological carbon cycle, nitrogen cycle, water cycle, it's always a cycle. What you're saying is, we'll take all the carbon and simply sequester it, and I'm taking it out of the cycle. And how is that better? So that's why I question that. But if you want to do it, fine. That's your policy. But I'm still better than petroleum because mine is negative and you're at 0. That's the answer to that thing. Yeah, I'm sure. So that question which you're asking is very correct because that's why we want it to be completely removed. So there's nothing remaining. So if microorganisms is capable of utilizing it without mutations, without any of the things you're talking about, and clearly in the standards, there is a criteria. You put barley, you put cereal Daphne, and you make sure that they are alive and grow as it should in a non-compost with this plastic in it, right? So you do that. But if you do it the right way, all of that carbon is being utilized by the microorganisms. So your plastic substrate is nothing but biological food or fuel for the microorganisms, and you let the nature play whatever role and cycle it does on the other side. And hopefully you do not affect the microbial diversity present. That's an excellent area of research which people should be doing, and fingerprinting and doing that. It's very little work has gone on in that area. I think she wants me to stop, so I better stop.